I am Jeroen van Meij and welcome to my lecture series on computer and network security. In this second video on asymmetric encryption, I will introduce the basics of the popular RSA encryption algorithm, which is named after its three inventors, Rivest, Shamir, and Adelman. And as I mentioned, RSA is named after its three inventors, Ron Rivest, Adi Shamir, and Leonard Edelman. They came up with RSA in 1977 at MIT. This is only 1 year after Diffie and Hellman first proposed this new type of encryption algorithms. However, later it was found out that a man named Clifford Cox, who was working for the British Secret Service, had already invented something very similar to RSA in 1973. This information, however, was kept classified until 1997. And even if RSA is over 40 years old, it is still the most widely used and popular asymmetric encryption algorithm. And this is thanks to its simplicity and elegance and its proven security. In RSA, each plain text block M is represented as a number. This number should be smaller than some given number n. As such, the block size is therefore less or equal to log2 of n plus 1 bits, because this amount of bits allows you to represent every number smaller than n. In practice, usually a block size of I is used where 2 to the ith is less than or equal to n and 2 to the ith plus 1 is greater than or equal to n. And to encrypt a message using RSA, we use some value e and take m to the eth power modulo n. To decrypt a message, we take some value d and take c to the eth power modulo n. So as you can see, this is a straightforward mathematical calculation. Obviously, m to the e to the d modulo n should also be equal to m. Otherwise, the encryption is not invertible. So, specifically, the sender and the receiver both know n. The sender should know e, and the receiver should know d. So if we use this approach for encryption, then the public key is the pair e and n, which is known to anyone, and the private key is the pair d and n, which should only be known to the receiver, and then only the receiver can decrypt the message. And I have a question for you related to RSA. Given a value of n equal to 2 million, what is the maximum allowed block size in bits? Is it A, 7 bits, B, 20 bits, C, 21 bits, D, 2 million bits, or E, none of the above? If you need some time to think about it, feel free to pause the video. And let's take a look at the answer. The right answer is B, 20 bits. Because with 20 bits we can represent any number up to 2 to the power 21 minus 1, which is over 2 million, and thus allows us to represent any value between 0 and 2 million. The main ingredients for RSA are therefore the values used in the public and private key, or E, D, and N. The question now is, how do we find a suitable value for E, D, and N, such that the property that m to the power E times D modulo n equals m, which is required for the encryption to be invertible? And the answer is given by Euler's theorem. Because if we assume that m and n are relative primes, then Euler's theorem states that m to the power totient n plus 1 equals m modulo n. Here the totient refers to Euler's totient function, which is the number of integers less than n that are relative prime to n. And from this statement, we can derive that given m to the power e times d modulo n equals m, we can then derive that e times d equals totient n plus 1 modulo totient n. Obviously, totient n plus 1 modulo totient n equals 1, so then e times d equals 1 modulo totient n, or d equals e power minus 1 modulo totient n. Or in other words, d is the multiplicative inverse of e modulo totient n. We have to, of course, here assume that d and e are relative prime to totient n, or that the greatest common divisor of totient n and e equals 1. The question that remains now is how can we guarantee that m and n are relative primes, which is a requirement for this derivation to be valid. If we now state, however, that n equals the product of two prime numbers p and q, then we can guarantee that m is relative prime to n if it is different from the values 1, p, or q. This is also desirable, this property that n is the product of two primes, because if n is the product of two primes, then the totient of n can be very easily calculated, being equal to p minus 1 multiplied by q minus 1. While for a general number n, it's very difficult to calculate the totient. Because of Euler's theorem, we now know that the invertible property of RSA is satisfied if E and D are each other's multiplicative inverse modulo totient n. And this gives us all the needed ingredients to calculate the public and private key for RSA encryption. We start with two primes P and Q. These are chosen by whoever generates the key and are kept private. N can then easily be derived by multiplying P with Q. N is a public value as it's part of the public key and can thus be shared with others. Then the key generator can choose some value E. The requirement is that E is a relative prime to the totient of n. As I mentioned, the totient of n can be easily calculated given that n is the multiplication of two primes P and Q, so its totient is P minus 1 multiplied by Q minus 1. Then D can be calculated from E by calculating E's multiplicative inverse modulo totient n. And this gives us the private and public key pairs, Dn and En. Something very important is that it should be computationally infeasible to derive P and Q from n. So if n is large enough, this is actually very difficult to calculate, because if an attacker would be able to calculate P and Q from n, they would be able to derive totient n, and this would allow them to find the private key. To make sure everyone understands the basics of RSA, I have two exercises to finish off this video. The first one, your goal is to calculate the private key given the prime numbers P and Q equal to 17 and 11, and part of the public key, namely the value of E, equal to 7. So my question is, what is the value of the private key D and N? Here you get some additional information and a hint. You can calculate the multiplicative inverse of E using the extended Euclidean algorithm, which you see summarized here on the right. And the second exercise is to perform RSA encryption using the parameters displayed here. So P equal to 17, Q equal to 11, E equal to 7, and D equal to 23. Perform RSA encryption for the plaintext message M equal to the number 88. This was it for this lecture. In the next video, I will talk about the details of RSA and how to efficiently perform the RSA calculations.